Hello, and welcome to the presentation for our final project. This is the LISE Lunar Rover team. Uh, I'm Keith McIntosh.
I'm Keenan Thungtrakul.
And I'm Alex Johnson. The project we decided upon was kind of a combination of two of our proposals. I had proposed a sample extraction system, and Keenan had proposed kind of a rover system. So we combined those two and kind of adapted this for our a senior design project that I'm part of. So the mission here is the rover is going to go to the moon. It's going to drill for some samples and collect them, and then return and give those samples to a lander.
So we decided to divide this rover into several different sub-assemblies in order to divide the work between the three team members. This was divvied into the rocker bogie, the wheel system, the frame and skin of the rover, the lander attachments, and the drill system, and some of the placeholder other parts. Now, the first system here is the rocker bogie subassembly that I created. This shows the full subassembly with its three wheels. This is the left half of the rover, showing each of the two articulated wheels and the one static wheel in the center. The way that the rocker bogie system works is that there are two different rockers. Here you can see the rocker that attaches to the main frame, number 4, and the back rocker, number 3. The middle wheel is static, and the front and back wheels are articulated, so as to allow for it to turn and move. Here is the full subassembly for the articulated wheels, showing the motor, the arm, and the full wheel. And here we can see better the motors for the drive motors, the arm, the articulation motors, and the wheel shaft.
This is the first part of our sample collection system. This is the chute subassembly, as we started calling it. Basically, the idea is that the drill will eventually run through this pipe here. And as it goes through, there's a brush that we'll see in the next slide. There's a brush in here, and it cleans off the drill. And then as when it collects enough samples, a valve closes, and nitrogen gas is pumped from this tank and pushes the samples up into this box here, which is our placeholder for the sample kind of packaging system. Originally, we were going to design that a bit more, but that was kind of, we had to cut that back to in order to complete this project. Here's a view of the exploded chute subassembly. You can see here's the brush. It fits inside this casing, and that all gets dropped down in this exit chamber. The next subassembly is the drill subassembly. This is the part that goes down and brings the regolith into the chute subassembly. So as the main parts of this, as we can see in the next slide, are the drill, the shelf, the cog wheels, and the cog motor. So basically there's a motor and a gearbox in here that turns two gears and kind of operates like a cog railway like you see in the mountains. And there's gear teeth along this. We were unable to do that because of kinematics. We wanted to make this animated, so we did not actually model the gear teeth, but there would be gear teeth here to allow it to move up and down along the shelf. Here's a short video showing how the animation works. So this is capable of moving up and down along the shelf, and then the next video is showing that there's a little gap in here on the back and the bottom where the brush would come in and sweep off samples as they're being brought up through the by the drill into the chute. So the drill initially is deployed through there, and then when it's deployed to whatever depth, it rotates and it pulls up the samples, and the brush brushes that off. As it gets deeper, the 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 drill will have to carry up the samples through the hole that is bored, and then the brush will brush it off.
So here we have the rover frame. This is where all the rover's electronics and batteries and internal workings will be placed into. The frame consists of a chassis that is covered by multiple panels. So the holes that you can see drilled into the top panel and the left side panel. There's a box here for a water molecule detection device, and then this hole here is for the axle for the rocker bogie suspension system. So here we have the exploded view of the frame, where we have the rear frame, number 9, and the rover chassis, number 10. There are multiple panels, as you can see here, 2, 4, 5, 6, 7, 1, and 3. They all mount to the chassis by means of rivets. And for the interest of simplicity, we just made it all aluminum. Now for the chassis itself, it's split into a wide variety of spars. There's a long frame spar, a short frame spar, a corner spar, a spar that holds the lander brackets and the nitrogen gas tank, and then a frame for the axles to slide into, an extra support structure for the shelf as the rover's in operation. So this is the rear frame. This is what's used to hold the rover's power generation system. It's called a radioisotope thermoelectric generator, or RTG. It's mounted against the backside of the frame. The rear frame consists of 4 unique pieces: a lower spar, a bottom spar, and 2 angled spars that are designed differently based on the where location they're placed on the frame. So the left angle spar would mount on the left side, right angle spar mount on the right side, and vice versa. This is a lander attachment subassembly, so this is what will hold the rover to the lander during flight. We thought it would be nice to have it designed like a prong, like how you see a forklift lifting a heavy pallet of warehouse storage. But instead, to keep it more secure, we thought of it to include a catch system, kind of like on a door, where the prong from the lander would slide in, and then these 2 pieces here would lock the prong into place. And once the lander touches down on the moon's surface, these latches will release, allowing the rover to roll out from the lander. The subassembly consists of 3 main parts: the prong bracket, the prong latch, and the motor casing that holds the spring joint and is able to rotate the latch in order to release the rover from the lander. These are some of the placeholder objects that we were initially going to make subassemblies for, but in the interest of time, we just decided to keep it simple. We have the radioisotope thermoelectric generator casing, a high gain radio antenna, a low gain radio antenna, the camera mast, and the box that houses the water molecule detection system, called a dynamic albedo of neutrons. This is just them labeled by what each one does: high gain antenna, low gain antenna, camera mast, dynamic albedo of neutrons, RTG.
So during the course of this project, one of the main objectives was to expose us and give us an excuse to learn a lot of advanced CATIA workbenches. So the CATIA workbenches that I used extensively were mainly kinematics and a bit of the GSD. So while I was designing the sample collection system, the piping, the tubing that came from the nitrogen tank into the exit chamber and the exit tubing that went from the exit chamber to the sample stowage box. I created those with the GSD workbench, and then I had to use a lot of constraints from the kinematics workbench in order to get the drill to deploy and rotate the way it does.
Originally, we were going to do like one big simulation of the sample collection system in action, but technical difficulties forced us to keep things simple.
We discovered there's a limit to how much you can store on your shared drive, in case any of you were wondering.
I used the GSD system in order to create some of the parts for the rocker bogie system, some of the rockers, in order to fit with the rest of the frame and fit within each other. It was fairly complicated.
So, in order to create the rover body, there were a lot of sheet metal parts, such as spars, frames, panels, and brackets. So, I thought it'd be a good idea for me to learn the sheet metal workbench, the generative sheet metal design workbench, to use to make all these parts. And, fortunately, every metal piece, every panel, every frame, every bracket was made in sheet metal design. Now, for the lander attachment, the bracket was created in sheet metal, but the latch had to be done in GSD because it was a complex shape, and thought I'd just go and apply elements of GSD to that component to find a better way to model it. And I also had to use the parametrization and formulas feature of CATIA because there were a lot of regular holes and stampings in the spars that had to be created, and I don't want to have to go in every single hole's definition and edit out what was needed. So I thought it best to go and just put a formula in there, put a parameter in there, and just edit that parameter if I have to change it.
So, for the T dynamics, we met mostly during class time, with the occasional exception, say recording a presentation to other teams, and we met outside of class to do that when we needed to. We distributed work. We tried to split it up as equally as possible. Some parts, like Keith's, were really complex just to create. You look at them and it's like, how are we even going to approach this? Keenan's parts were, how are we going to use stuff like sheet metal and formulas like he talked about, and my parts were a lot of, how are we going to make this with kinematics in mind. So we kind of took three different approaches and combined them to try to create this finished product. So thank you very much. We hope you enjoyed our presentation. Good luck on the rest of your finals.
Yep, and have a wonderful summer.